Welcome to the YouTube channel, Contact Center Knowledge Hub, your one-stop solution for expert guidance, best practices, and actionable knowledge in the world of contact centers. Explore, learn, and enhance contact center skills. Let's take a clear and practical look at simple linear regression, or SLR, in the context of forecasting. Simple linear regression is one of the most fundamental forecasting techniques. It helps us understand and predict how one variable influences another by modeling their relationship as. In this method, we work with two variables: an independent variable, known as X, and a dependent variable, known as Y. In forecasting applications, time is almost always used as the independent variable, X. The metric, such as call volume, average handle time, shrinkage, revenue, or any other business KPI, becomes the dependent variable, Y. By analyzing how this metric behaves over time, SLR allows us to draw a straight-line relationship and extend that line into the future to. In summary, simple linear regression connects time with the metric you're forecasting, using a clean, easy-to-understand linear pattern to project future values. Let's understand the conceptual foundation of simple linear regression, or SLR. SLR is based on three key assumptions. First, it assumes that the relationship between time, represented as X, and the metric you want to forecast, represented as Y, follows a straight. Second, it assumes that as time moves forward, the metric changes at a constant rate. This constant rate is known as the slope. And third, it assumes that future values can be estimated simply by extending this straight line into the future. Regression line is written as y hat equals a plus bx. Here's what each component means. Y hat is the forecasted value. A is the intercept. This represents the baseline value when x equals 0. B is the slope, how much the metric changes for each unit of time. And x is the time period, such as 1, 2, 3, and so on. This simple equation forms the core of linear forecasting and helps us project how a metric will behave over time, assuming the trend continues in a straight line. Now let's understand when simple linear regression is the right forecasting method to use. You should use SLR when a few clear conditions are met. First, there must be a consistent upward or downward trend over time. For example, if call volumes are increasing by around every month, SLR is a suitable choice. Second, the relationship between the independent variable, X, and the dependent variable, Y, should appear linear. A simple example is average handle time steadily declining as automation improves processes. Should be no strong seasonality in the data. Simple linear regression cannot handle weekly, monthly, or yearly cycles on its own. If seasonality exists, you'll need more advanced models. And finally, your dataset should include at least 10 to 12 times. This ensures stability when calculating the slope and the intercept, making your forecast more reliable. When these conditions are met, simple linear regression provides a clean, effective, and easy-to-interpret forecasting solution. Let's continue exploring the mathematical components that power simple linear regression. We will look at three key elements: the slope, the intercept, and the forecast equation. 1. The slope, represented as b, the rate of trend change. The formula for the slope is b equals n times the sum of x times y minus the sum of x times the sum of y, all divided by n times the sum of x squared minus the square of the sum of x. The slope tells us how quickly the metric is rising or falling over time. Here's what it means in practice. If B equals positive 200, call volume grows by 200 calls every month. If B equals negative 4, average handle time falls by 4 seconds each month. So the slope is the engine that drives the upward or downward movement of your forecast. 2. The intercept, represented as the baseline value. The formula for the intercept is A equals the sum of y minus b times the sum of x, all divided by n. The intercept represents the estimated starting point, that is, the value of y when x equals 0. In time series forecasting, we rarely interpret this value literally. Its purpose is mostly to position the regression line correctly on the graph. 3. The forecast equation. The complete forecast equation is y hat equals a plus bx. This is the equation you use to calculate future values. Here, x represents the future time period. For example, to forecast month 13, you simply plug in x equals 13. This equation combines the intercept and the slope to generate a clear, mathematically grounded prediction of where your metric is heading. Step 1. Collect your data. This is where every solid forecast begins. Start by gathering your historical information, for example, monthly call volumes for the past 12 months. Think of this as building your foundation. The stronger and cleaner more accurate your forecast will be. So before we move forward, make sure your dataset is complete, consistent, and ready to drive your regression model. Step 2. Assign the time index. In this step, we convert each month into a numerical value so the regression model can understand the sequence of time. Start with January as 1, February as 2, March as 3, and continue this pattern until December, which becomes. This numbering helps the model identify how values change as time moves forward. Remember, assigning a time index is essential because regression needs numerical inputs to detect trends over time. Step 3. Compute the slope, represented as b. The slope shows how much the metric changes with each step in time. To calculate it, we use the correlation between the time index and the metric you are forecasting. A positive slope means the value is rising over time. A negative slope means the value is declining. In simple terms, the slope tells us the direction and the strength of the trend. Step 4. Compute the intercept, represented as A. The intercept is the starting point of our regression line. It tells us the expected value of the metric when the time index is 0. We calculate the intercept by combining the average of the metric, the average of the time, and the slope we computed in the previous step. Think of the intercept as the baseline level from which all future trend movements begin. Step 5. Build the regression equation. Now that we have both components of the regression line, the intercept A and the slope B, we can put them together to form the forecasting equation. In this example, the intercept is 18,200 and the slope B t. So our regression line becomes y is equal to 18,200 plus 250x. This equation tells us how the forecasted value changes as the time index increases. Every time x goes up by 1, the predicted value increases 50. This is the final formula we will use to generate future forecasts. Step 6. Forecast the future periods. Once we have the regression equation, we simply plug in the time index for the period we want to predict. For example, to forecast month 13, we substitute x equals 13 into the equation. So the calculation becomes y is equal to 18,200 plus 250 multiplied by 13, which gives us a forecast of 21,450. This value represents the predicted metric for the 13th month, based on the trend identified in our historical data. Step 7. Evaluate the accuracy of your regression model. After building your forecast, it's essential to check how well the model is performing. We do this using standard accuracy metrics. First, MAPE, mean absolute percentage error. The average percentage difference between actual values and predicted values. Second, WAPE, weighted absolute percentage error. This adjusts the error based on the size of the actual values, making it more reliable for contact center metrics. Third, RMS, mean square error. This tells us how large the typical forecasting error is. Lower values indicate better accuracy. And finally, R-squared, also called the coefficient of determination. It explains how much of the variation in the metric is captured. The closer R-squared is to 1, the stronger the model. Evaluating these metrics helps ensure your forecast is both credible and dependable. Now, let's understand how R-squared helps you interpret the quality of your forecast. R-squared ranges from 0 to 1, and it tells you how well the regression line fits your historical data. A value above 0.90 indicates an excellent trend fit. 0.70 and 0.89 represent a good fit. If it falls between 0.50 and 0.69, the trend fit is moderate. And anything below 0.5 means the trend is weak, and linear regression may not be reliable for forecasting. Here's an example. If your R-squared value is 0.82, it means that 82% of the variation in call volume is explained by the time-based trend. In simple terms, a higher R-squared means your forecast is more trustworthy and grounded in real data patterns. Let's look at how simple linear regression is used in real-world contact center operations. Application 1. Call volume forecasting when there is no seasonality. If call volume shows a steady month-over-month increase, simple linear regression can accurately project future growth based on that trend. Application 2. AHT forecasting during automation or digital adoption. As automation improves, average handle time often drops in a smooth, linear pattern. SLR helps you quantify how fast AHT is decreasing and predict future levels. Application 3. Shrinkage trend forecasting. If shrinkage is slowly reducing due to better planning, reduced burnout, or lower overtime, a linear model can capture the long-term downward trend. Application 4. Productivity KPIs such as contacts per FTE. When performance improves steadily due to coaching, training, or AI-assisted tools, SLR helps measure and forecast those productivity gains. Application 5. Cost per contact. If operational efficiency programs consistently bring costs down over time, a linear trend model provides a reliable forecast for budgeting and planning. These applications show how simple linear regression can support smarter decision-making across forecasting, staffing, budgeting, and performance improvement. Let's go through the key advantages of simple linear regression in a contact center environment. First, it's easy to compute and easy to interpret. Even non-technical managers can clearly understand what the model is saying. Second, it provides a clear trend and a clear. You instantly know whether the metric is rising or falling, and exactly how fast it is moving. Third, it works extremely well for stable, long-term trends. When the pattern is predictable and consistent, simple linear regression gives reliable results. Regression line is mathematically optimal. It minimizes the sum of squared errors, ensuring the best possible straight-line fit across the data. And fifth, it supports strong statistical testing. Tools like the t-test, p-values, and R-squared allow you to diagnose model reliability with confidence. These advantages make simple linear regression a powerful, transparent, and trusted forecasting tool. Let's go through the key advantages of simple linear regression in a contact center environment. First, it's easy to compute and easy to interpret. Even non-technical managers can clearly understand what the model is saying. Second, it provides a clear trend and a clear. You instantly know whether the metric is rising or falling, and exactly how fast it is moving. Third, it works extremely well for stable, long-term trends. When the pattern is predictable and consistent, simple linear regression gives reliable results. Regression line is mathematically optimal. It minimizes the sum of squared errors, ensuring the best possible straight line fit across the data. And fifth, it supports strong statistical testing. Tools like the t-test, p-values, and r-squared allow you to diagnose model reliability with confidence. These advantages make simple linear regression a powerful, transparent, and trusted forecasting tool. Simple linear regression is a great starting point, but real-world demand forecasting often requires more advanced techniques. Here are 4 powerful enhancements that build on the basic SLR framework. First, multiple linear regression, or MLR. This method includes additional predictors that influence demand. For example, marketing spend, holiday flags, weather conditions, pricing changes, agent count, or even digital adoption percentage. By including these variables, the model captures more real-world drivers and improves accuracy. Second, polynomial regression. This enhancement allows the trend to curve instead of staying perfectly straight. It's useful when demand accelerates or slows down over time. Third, seasonal regression models. These models add dummy variables for months, weeks, or days to capture repeating seasonal cycles. If your data has strong seasonality, this approach dramatically improves forecast quality. And fourth, AI hybrid models. Modern neural networks often use regression as a baseline and then add nonlinear layers on top. This combination captures both linear stability and complex real-world patterns. Together, these enhancements transform simple regression into a robust, real-demand forecasting engine. Let's walk through a complete practical example of using simple linear regression to forecast call center call volume. We begin with 6 months of historical data. Month 1, 20,000 calls. Month 2, 20,400. Month 3, 20,900. Month 4, 21,200. Month 5, 21,600. Month 6, 22,100. Using this data, simple linear regression identifies the trend. The slope, represented as B, is approximately plus 400 calls per month. This means calls are growing steadily every month. The intercept, A, is approximately 19,600. This represents the baseline call volume when the time index starts. With these values, the regression equation becomes y is equal to 19,600 plus 400x. Now let's forecast month 7. We substitute x equals 7 into the equation. Y is equal to 19,600 plus 400 times 7, which equals 22,400 calls. This forecast aligns perfectly with the natural upward trend in the historical data. Simple linear regression helps us quantify that trend and project it forward with confidence. Let's simplify how to interpret your regression results. First, look at the slope. If the slope is positive, the metric is increasing over time. If the slope is negative, the metric is decreasing. And if the slope is 0, the metric is stable, there is end. Next, check the R-squared value. If R squared is high, it means the trend is reliable and the model explains most of the variation in the data. Finally, review the p-value. If the p-value is less than 0.05, the regression is significant. This tells you the trend is real and not just due to random noise. These three signals, slope, R squared, and p-value, give you a quick and clear interpretation of your forecast model. Let's wrap up with the key takeaways from simple linear regression forecasting. First, simple linear regression models the relationship between time and a metric using a straight line. Second, it is ideal for trend-only, non-seasonal forecasting, where the data moves consistently upward or downward. Third, it provides highly interpretable parameters, such as the trend slope and the baseline intercept, making analysis easy to explain to stakeholders. Fourth, forecasts are created by extending the regression line into future periods, using the same trend behavior seen in historical data. Fifth, linear regression should be avoided when patterns are seasonal, nonlinear, or unstable, because a straight line cannot capture those complexities. And finally, simple linear regression is best used as a foundational building block that feeds into more advanced forecasting models, including seasonal, multivariable, and AI-driven approaches. These insights help you understand when and how to use SLR effectively in real-world forecasting. Thanks for watching my YouTube channel, Contact Center Knowledge Hub. If you found this helpful, don't forget to like, share, and subscribe for more insights. See you in the next video.